40 light-years from Earth, in a small, dim red dwarf's glow, lies a system of 7 rocky worlds orbiting in tight, gravitational embrace. These are the TRAPPIST-1 planets, a family that has captivated astronomers and dreamers alike. Each transit, each flicker of light shows us more than just motion. It hints at possibility. Among them, one planet stands out, TRAPPIST-1e. It is neither the innermost nor the outermost of its siblings. It sits in the star's Goldilocks zone, a region neither too hot nor too cold, where liquid water might survive. Earth-sized, rocky, temperate. Now, after years of speculation and observation, something remarkable is emerging. Strong hints, perhaps the strongest yet, that TRAPPIST-1e may not be a barren, airless rock. It may have an atmosphere, not just any atmosphere, one with enough structure and composition to change our expectations of what is possible around red dwarf stars, to bring TRAPPIST-1e closer to being a world we might, one day, understand not just from afar, but in depth. Red dwarfs are small. They are faint. They live longer than stars like our Sun. But they are also volatile, prone to flares, magnetic storms, and strong ultraviolet, UV, and X-ray emissions. For a planet like TRAPPIST-1e, orbiting close to its star, this means exposure to intense radiation, which can strip away atmospheres, especially hydrogen-rich ones, over geological time. Early observations of other TRAPPIST-1 planets, particularly the innermost ones, B, C, and D, suggested they're likely bear rocks or have very thin atmospheres. These results raised serious doubts. Can a planet around such a star hold onto an atmosphere at all? But TRAPPIST-1e sits somewhat farther out, where stellar radiation is still strong but less extreme. This gives hope, a chance that an atmosphere, if present, can survive. And in 2025, using the James Webb Space Telescope, JWST, astronomers have begun seeing data that suggests the possibility is real. In 2023, TRAPPIST-1e was observed during 4 separate transits using JWST's NIR-SPEC PRISM instrument. Each transit allowed starlight to pass through the planet's atmosphere, if one exists, filtering it in ways that subtly shift the spectrum, the distribution of light by wavelength. These shifts carry fingerprints of atmospheric molecules, if they are present. The results are tentative but encouraging. The planet does not show signatures consistent with a thick, hydrogen-dominated primordial atmosphere, which many gas giants possess. Such an atmosphere would be puffy and would produce strong, easily detectable spectral features. TRAPPIST-1e's data appear to rule that out. Similarly, atmospheres like those of Venus or Mars, rich in carbon dioxide at high pressures, seem less likely. Models that assume a Venus-like or Mars-like CO2-dominant atmosphere are inconsistent with the patterns observed in the spectra. The data do not definitively confirm the presence of an atmosphere either. There is room for the possibility that TRAPPIST-1e is bare or has a very thin secondary atmosphere composed of heavier gases, nitrogen, maybe smaller amounts of other gases. Signal variation across different transits and interference, stellar contamination, from the host star's activity make it hard to claim certainty. These observations are already narrowing down the possible scenarios, sharpening the image of what TRAPPIST-1e might be like. So if TRAPPIST-1e has an atmosphere, what might it look like? Several models suggest it would be a secondary atmosphere, one that formed after the planet lost its primordial gas envelope. Sources could include volcanic outgassing, sublimation from the surface, or release of gases through interior geochemistry. Such an atmosphere would likely be composed mostly of nitrogen, possibly with trace amounts of other gases like water vapor, carbon dioxide, and perhaps methane, similar in broad strokes to Earth's early atmosphere or Titan in our solar system. Climate models and general circulation models, GCMs, suggest that if the atmosphere has around 1 bar or less of pressure and is nitrogen-rich, it could support redistribution of heat between the planet's day and night sides. Because TRAPPIST-1e is likely tidally locked, one side always facing its star, one side in permanent night, the atmosphere plays a critical role. Without an atmosphere, the day side would scorch and the night side freeze. With even a modest atmosphere, heat could flow, moderating the extremes. Clouds and hazes complicate everything. They can mute spectral signatures, mask molecular absorption lines, and change the planet's temperature profile. Some models show that clouds in the upper atmosphere could obscure key features, making it appear more Earth-like even if it isn't exactly so. If TRAPPIST-1e does have a nitrogen-rich atmosphere as the data allow, then it becomes one of the most compelling habitable zone planets yet known. An atmosphere provides pressure, allowing for liquid water to exist if temperature permits. It shields the surface from harmful radiation, and it regulates climate. Even a thin atmosphere can reduce temperature extremes. Moreover, if there is enough greenhouse effect, the habitable zone shifts outward, making such planets more likely to have moderate climates rather than being permanently frozen or scorched. These findings also suggest that habitability around red dwarfs, once considered unlikely due to their volatile stars, may be more viable than previously thought. If TRAPPIST-1e retains an atmosphere, it means rocky planets in the habitable zones of red dwarfs can survive threats like stellar flaring and atmospheric loss, depending on their composition, magnetic field, and history. But habitability is not just about atmosphere. It's about water. Liquid water, stable temperature, the right chemical recipe. So far, TRAPPIST-1e remains consistent with having enough mass and rocky composition to support an ocean or surface water under proper atmospheric conditions. But that is still speculative. The evidence is strong, but far from conclusive. One major obstacle is stellar contamination. TRAPPIST-1 is an active red dwarf. Its surface is marked with star spots. Its brightness fluctuates due to flares, and those variations can mimic or mask atmospheric spectral features. Differentiating what comes from the star versus what comes through the planet's atmosphere is difficult and demands many repeated observations. Another challenge is measurement sensitivity. Even with JWST, detecting weak molecular absorption when the atmosphere is thin or has haze is very hard. Many models show that detection of gases like water vapor, methane, or carbon dioxide may require dozens of transits, planetary crossings, to build up enough signal. Clouds/hazes can wash out features. There's also the possibility that what we think is atmospheric signal is actually an artifact or a misinterpretation, maybe due to uncorrected instrument effects, or because the planet is essentially airless and we're only seeing heat or reflection anomalies, not absorption by gases. Scientists are cautious. They rule out some scenarios, but don't quite confirm others. Even as the uncertainties weigh heavily, the direction of progress is clear. TRAPPIST-1e is now one of the best candidates in the galaxy for a rocky, temperate, possibly habitable planet with an atmosphere. Upcoming observations will deepen our understanding. JWST is expected to observe additional transits. The number may increase from 4 to upward of 15 or more, which will improve signal-to-noise and allow better corrections for stellar activity. Scientists will also use different instruments and wavelengths, combining transmission and emission spectra, looking for molecular absorption features of gases like CO2, CH4, water vapor, nitrogen, possibly even oxygen or ozone if lucky. Each detection or non-detection narrows what kind of atmosphere could exist. New ground-based telescopes like Extremely Large Telescope, YELT, and space missions in the future may play a role. If at any point we confirm a stable, Earth-like atmosphere, we'll have moved from speculation to evidence. TRAPPIST-1e will become more than hope. It will become one of the best places to look for life beyond Earth.